Hello, wonderful learners. Here's a curious thought. Did you know that when fluids flow, they're actually juggling three forms of energy all at once? It's like a fluid is an acrobat balancing pressure, speed, and height to keep its act perfect. Speaking of juggling, here's a quick joke. Why did the fluid break up with the solid? Because it couldn't handle the pressure. Now, let's dive into Bernoulli's principle, which essentially says that for a fluid flowing steady, without squishing or stickiness, in other words, incompressible and non-viscous, the total mechanical energy along a streamline stays constant. Imagine energy as the fluid's budget, and it spends it on three things: pressure energy, kinetic energy from its speed, and potential energy from its height. Mathematically, this is expressed as pressure P plus 1/2 times fluid density ρ multiplied by velocity squared plus the product of fluid density, gravitational acceleration g, and height h equals a constant. Here, P stands for pressure energy, 1/2 ρ v squared is the kinetic energy per unit volume, and ρ g h is the gravitational potential energy per unit volume. So whenever you see a fluid flowing, remember, it's all about conserving this total energy neatly balanced, just like a perfectly managed checkbook. Now, to understand where Bernoulli's equation comes from, picture fluid flowing between 2 points along a pipe with steady flow. Think of these cross-sections as checkpoints where fluid's energy is being counted. The fluid does work due to pressure and gravity, and in response, its kinetic energy changes. The net work done by pressure forces is pressure at point 1 multiplied by area 1 times the small distance moved dx1 minus pressure at point 2 times area 2 times dx2. This net work equals the change in kinetic and potential energies of the moving fluid mass. Applying the law of energy conservation between these 2 points leads us step by step to Bernoulli's beautiful expression: pressure plus 1/2 ρ v squared plus ρ g h remains constant along that streamline. But remember, this derivation holds perfectly only under ideal conditions, when the flow is steady, the fluid incompressible, and the viscous drag is negligible. It's like assuming your bicycle gears never slip and the road is perfectly smooth, just a perfect theoretical ride. Let's peel back the meaning of each term in Bernoulli's equation as if we are examining the fluid's energy wallet. First up, the term P, pressure, which represents energy stored due to fluid compression. This is also called pressure head. Imagine squeezing a sponge. That stored up energy pushes back, and that's what pressure energy is all about. Next, the kinetic energy term, 1/2 times ρ times velocity squared, comes from the fluid's bulk movement. The faster the fluid streams, the more kinetic energy it carries, much like a speeding cyclist has more energy than someone walking. Lastly, ρ times g times h captures the potential energy from the fluid's height in a gravitational field. The higher the fluid, the more potential energy it can convert to motion, just like a roller coaster at the peak ready to zoom down. Importantly, all these terms share the same units, energy per unit volume, that is joules per cubic meter, so they add up sensibly in the fluid's energetic budget. Now, you might wonder, where do we see Bernoulli's principle in action? Well, look no further than airplanes soaring high in the sky. The wings are designed so that air moves faster over the curved top, lowering pressure compared to beneath the wing. This pressure difference lifts the plane. Yes, Bernoulli's principle helps keep pilots flying. It's also the secret behind devices like venturi meters and carburetors, where fluid speed changes are cleverly used to measure or regulate pressure. Imagine a narrow constriction in a pipe. The fluid speeds up there, but to keep energy conserved, pressure drops. In fact, velocity at point 1 is less than at point 2, so pressure at point 1 is greater than pressure at point 2. That's Bernoulli's equation talking. So next time you see a hummingbird hover or hear a carburetor purr, Remember Bernoulli's clever fluid dynamics at work. Consider a pipe that narrows in the middle, a tapered tube. As fluid moves through this pinched section, its velocity increases and pressure decreases following Bernoulli's principle. But there's another important rule, the equation of continuity, which tells us that the product of cross-sectional area and velocity at one point equals the same product at another point, that is area 1 times velocity 1 equals area 2 times velocity 2, making sure no fluid magically disappears or appears. Substituting this into Bernoulli's equation gives us pressure at 1 plus half rho velocity 1 squared equals pressure at 2 plus half rho velocity 2 squared. This relationship helps us calculate velocities and pressures at different points along the pipe, vital for engineers designing systems like water supply or air conditioning ducts. Picture water speeding up through a narrow section, pressure dropping there, and that's the magic of combined continuity and Bernoulli principles. Now, imagine a clear diagram showing streamlines, which are like the traffic lanes of fluid flow. When the streamlines bunch closer together at a constriction, the fluid moves faster and pressure drops. This visual tells us about the inverse relationship between pressure and velocity along a streamline. The simplified Bernoulli form for horizontal flows ignores height changes, so pressure plus 1/2 times rho times velocity squared equals a constant. This form is super handy when dealing with horizontal pipes or channels where height doesn't matter much. So, the closer the lanes squeeze together, the faster the traffic moves and the lower the pressure pushing sideways. This intuitive image helps us grasp why your garden hose nozzle works better when squeezed, fluid speeds up, reducing pressure, spraying water farther. Let's apply Bernoulli's principle with a classic example, water flowing out from a tank through a hole located at depth h. Imagine a big open tank, water surface open to the atmosphere, so velocity there is nearly zero and pressure is atmospheric pressure. At the hole, pressure is also atmospheric since it opens to air, but water jets out at some velocity using Bernoulli's equation, atmospheric pressure plus fluid density times gravitational acceleration times height h equals atmospheric pressure plus 1/2 fluid density times velocity squared. Cancelling atmospheric pressure from both sides and solving for velocity, we find velocity equals square root of 2 times gravitational acceleration times height h. This formula is known as Torricelli's law and explains why water gushes faster from deeper holes. This is the same principle behind water fountains and even tears streaming from your eyes. Well, maybe not quite the tears, but you get the idea. To really believe Bernoulli's principle, scientists use experiments with devices like pitot tubes and venturi meters. These tools measure fluid speed and pressure inside pipes. The data confirms the inverse relationship. As velocity increases in a narrow section, static pressure decreases because energy is conserved. On a graph, pressure lines slope downward as speed lines slope upward, matching the formula that change in pressure equals 1/2 times fluid density times velocity squared at point 2 minus velocity squared at point 1. This neat experimental validation means Bernoulli's principle is not just theory, it's a reliable tool engineers use to design everything from airplane wings to pipeline systems. So, to wrap up our journey through Bernoulli's principle, the total mechanical energy of a flowing fluid equals pressure plus 1/2 times density times velocity squared plus density times gravitational acceleration times height, and this sum stays constant along a streamline. With practical results like velocity equals square root of 2 times gravitational acceleration times height for free jets, and the continuity equation area 1 times velocity 1 equals area 2 times velocity 2 ensuring mass conservation, we see how fluid speeds and pressures are linked. The principle assumes steady, incompressible, and non-viscous flow, making it perfect for many, but not all, real-life situations. Bernoulli's equation shows that when a fluid speeds up, pressure goes down, a key insight for engineers and scientists alike. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.